it's 10:30. Let's see more students in. Okay, everybody is in. Good. All right. So I guess I need to start the class because it's 10:30. I'm not seeing that many students today. It's okay. Maybe they can refer to my notes on one notebook. Yeah. All right. That's fine. All right. So let's go ahead and continue to see a few more problems on testing of hypothesis. Again, I'm telling you, chapter 14 deals with the two things. One is the confidence limits for unknown population mean mu. So we are basically constructing the confidence limits for the population mean mu based on the single sample data given to us. So obviously the data is going to have the sample size, which is n, and then the sample of n observation is going to give you the sample mean. So x bar is going to be there, and then you will also be given sigma. On top of that, you are going to be given one more number. That number is the confidence level, which is nothing but your probability. So with the maximum confidence level based on the single sample data, you're trying to provide the confidence limits for the unknown population mean mu. All right. So that was the first part of your chapter 14 material. So we basically found the lower limit and the upper limit, and either side from the center you have the margin of error. So that gives you the cutoff point for the lower limit and the cutoff point for the upper limit. So remember, we always try to maximize our level of confidence. We don't want to go below 80%. So our level of confidence, which is nothing but my probability, is always going to be a bigger number. Because if I'm saying something with a certain level of confidence, so my probability should be higher, and I am keeping the biggest number for that, say 90, 95, 99. Those are the most commonly used numbers, but still I can go up to 80%, not below that. Okay. All right. So that is the first part, as I said, that was discussed on Monday. And then Tuesday, yesterday, we talked about how to find the sample size. So with the concept or with the deductions that as n increases, your sigma over square root of n decreases, using n excess, that's right. And so as this, your margin of error is going to be increasing. So they go in the opposite direction. N and margin of error, they go in the opposite direction. All right. And how about the confidence level and the margin error? Bigger, as confidence level gets bigger, you a bigger margin of error, or you can say the margin of error stretches, and as a consequence, you will have a wider confidence limits. But on the flip side, if you reduce your confidence level, your margin of error shrinks. So I want you to learn all these deductions or the results in order to answer your true or false question. Okay, so you should know that these changes when you change your sample size, when you change your confidence level, you should know what is going to be the change in your confidence limits. All right, so that's why I am telling you, you should be able to answer the true or false question only if you are very strong in this material. All right. So when you are going to increase your sea level, then your margin of error stretches, and as a result, your confidence limits gets wider. So because they are pulling each other, the confidence level, the margin of error, and the sample size, they are all pulling each other with a condition sigma is known. So I am going to be finding what would be the sample size n, or how large the sample size is going to be if the margin of error is given. So that's where we have seen chapter 15 on Tuesday, how to find the sample size n. So there is a formula here. The formula here is n is equal to z star sigma over margin of error the whole square. So again, what I'm saying is, yes, these three guys, they pull each other. The sample size and the confidence level and the margin of error on either side from the center, they are pulling each other. They're playing a game of tug of war. So we are going to be finding the sample size n with sigma, with your C level given in the problem, with your margin of error given in the problem. Usually the margin of error will come with plus or minus, because it's going to be the number on either side from the center, or sometimes you will also be given the keyword within, or sometimes you will be given twice width is equal to margin of error. Sorry, twice margin of error is equal to width, and that way, if the width is given, then you can get the margin of error is going to be width over 2. So if you are given the width is the same as the length of the interval, which is the upper limit minus the lower limit. So suppose if the width is given, I mean to say, uh, that is twice the margin of error, and then half of it is going to be equal to the margin of error. All right. So what, anyways, whatever it is, so you have to read the problem. In all cases, you have to read the problem, whether the MOE is given or twice the MOE is given. And on top of that, you can also imagine the plus or minus sign, and that's going to be on either side from the center, and within is another keyword that can be used for margin of error. That's right. So if these numbers are given, then you are going to predict how big the sample should be, how large the sample should be. So yesterday we have seen this formula on chapter 15, and it is given by z star times sigma over MOE the whole square. So again, I'm telling you, do not forget to square that. The squaring that number is very important. Otherwise, you are solving for square root of n. We don't want to get the value for square root of n. We want the value for n. So okay, so Isabella, I think you are sending me some message. I will answer it later. Okay.
Thank you.
Yeah. Sample size n is equal to z star times sigma over margin of error mo the whole square. Okay. Remember, square root of n times square root of n is n. So we don't want to solve for square root of n. We want the value for n, which is our sample size. So that's why I'm squaring on both sides. So you will get this formula. So this is what we have seen in chapter 15. All right. So we have seen part of chapter 14, and then in testing the 5%, you are given a recipe. So basically, we are going to be testing the claim or the sentence or the statement on mule. So this is what is going to be done on testing of hypothesis. Again, it is going to be done based on a single sample. All right. So in testing of hypothesis, you're trying to find evidences provided by the sample data of statement on you. You have to say whether the statement is good to go, or it's not going to be accepted, or it's going to be rejected, or do not accept, do not reject, whatever it is. So that is what is going to be tested in testing the hypothesis. Okay. So basically, again, as I said, we are trying to find evidences for the statement. Is that statement is accepted? Is that statement is good to go? That's right. So any testing of hypothesis involves in any subject, there is going to be a recipe for that, whether it is a chemistry subject, whether it is a physics subject, anything. If it is a test, that means it involves some recipe. Okay, so what is a recipe here? So we are given a few steps here. So the step one says the null versus alternative. In math 130 level, we always keep our null hypothesis as mu equal to mu sub 0. So that's always going to be equal to the number coming from the population. That's right. And against the null hypothesis, or in opposite or in negation to the null hypothesis, we are going to deal with the three signs. One is going to be the less than sign, the other one is greater than sign, and the third one is a not equal to. So in opposite to the null equal to sign or the null hypothesis, in math we always discuss about the three signs. It could be less or could be greater or it could be not equal to. So not equal to case includes both the less than and greater than sign. But each one is given a name here in statistics. So the alternate hypothesis is set into or same or both are same. Okay, you can denote it as lowercase a or uppercase a, doesn't matter. Okay, a stands for alternative anyways. So if it is mu less than mu sub 0, it will be called as your left tail test, and then mu greater than mu sub 0 is called as the right tail test. Mu not equal to mu sub 0 is called as the two tail test. All right. So the two-tailed test includes both a smaller and bigger value of a mu sub 0. As I said, it's going to be on both sides. It includes both cases. All right. All right. So next one is the test statistics. So I want you to recall the z-score that we introduced in chapter 13 for quantitative variable. So this is the z-score that's going to be calculated as step number 3. So bring the z-score based on the sample data that you are given. So the z-score is going to be done, and after that you are going to be doing the probability. As always, once you are done with the z-score, you're going to be doing the probability. So that's what is going to be done here in the next step. But before that, we are taking a detour, tiny detour of introducing a new number called alpha. So what is the new number that we are introducing? The new number is the level of significance, which is a Greek alpha letter, the alpha, and that signifies the probability of a type 1 error. So another concept is coming in, the type 1 error. What is the type 1 error? The type 1 error is rejecting the null hypothesis when it is true. So in any decision making problem or in deciding which statement is going to be accepted or rejected, because we are doing the testing of hypothesis, we are going to be deciding which statement is good to go. So that way we are going to be making a decision here based on the claim, right? So there are two types of errors that's going to be totally inevitable. What are they? Type 1 error and type 2 error. So the type 1 error is you are going to reject your null hypothesis, or you can say the statement on mu is going to be rejected when it is a true statement. So that is one type of error that you can commit. The second type of error is accepting the wrong statement when it is false. So that is another type of error that you can commit in testing of hypothesis or in any decision making problem. So if I go deep into that with an example here written as H sub 0 as the defendant is innocent, the defendant is not innocent, so it's not guilty, is guilty. So with that, I'm making a tiny table here. So I noticed that two scenarios are giving me a correct decision, no question about it. So how about the other two scenarios? So those are called the type 1 and type 2 error. So again, in short, rejecting the null hypothesis when it is true. So that is the technical term for type 1 error. Rejecting the null hypothesis when it is a true statement is called as type 1 error. On the flip side, I am accepting the wrong statement or accepting H sub 0 or about the mu when it is a false statement. That's going to be called as type 2 error. So this one is not included for you. So this is going to be discussed in a higher level statistics class. So only this one is going to be included for your Mark 130 because you are learning the introduction to statistics. And this is the first time you are learning the testing of hypothesis. So let's not worry about the type 2 error, okay? That's going to be the higher level classes. That's fine. So the type 1 error, I am fixing it as alpha equal to, usually that number is going to be 5 percentage or 1 percentage or 10 percentage, or unless otherwise some other number, different number given in the problem, it's going to be a preset number. Like your all confidence level as a 90, 95, 99 percentage, your alpha, the level of significance, we don't want to make it as a bigger number. So that's going to be usually the smaller number, say 1 percentage, 5 percentage, or maximum of 10 percentage. Again, there is a connection between your alpha and your confidence level. Those two numbers are complementing each other, all right? So if I'm talking about the 90 percentage confidence limits for mu, obviously the 10 percentage is going to be my level of significance, which is the alpha. If I'm making my 95 percentage confidence limits for mu, the remaining 5 percentage is going to be used for my alpha, and that's going to be called as my level of significance. In other words, that's also going to be called as the rejection zone or the rejection region. If I make my 99 percentage confidence interval for my population mean mu, so the remaining 1 percentage is going to be given to the rejection region, and that's what I call it as my alpha, the level of significance. All right. So remember always, we are going to maximize the confidence level, but on the flip side, we are trying to minimize my alpha. We don't want to maximize the mistake that we are doing because it's already a type 1 and type 2 error. We don't want to maximize the mistake that we are committing. We need to minimize as minimum as possible, right? So that's why this alpha is going to be the smallest number, say 5 percentage, 1 percentage, or 10 percentage, unless otherwise is given a different number in the problem. All right. So next step in my testing of hypothesis is, now I have two probability values. One is alpha, one is the z-score probability value. So the z-score probability value and alpha, they are going to be compared. I don't have to talk much about the probability value because you know how to get the probability value that you learned in chapter 13. Second was option number 2, normal CDF -8 comma the z-score is going to be used for the left tail test, and then normal CDF z-score comma 8 is going to be used for the right tail test. When it comes to the two tail test, remember the region is going to be on both ends. So you are going to be using, because the two-tail test includes both options, mu less than mu sub 0 and mu greater than mu sub 0. So it's going to be twice normal CDF z-score comma 8 if your z-score is a positive number. Or it can be P equals 2 times normal CDF for -8 comma z-score if the z-score happens to be a negative number. That's right. So this is what is my recipe saying about the z-score, the p-value. All right, the next one, you are going to compare the two p-values. If your p-value is less than or equal to alpha, you are going to reject your null hypothesis. So basically this diagram, see, if your alpha value is falling in the rejection zone, that means you are going to be rejecting your null hypothesis. I'm zooming that picture. Alpha is given as some 5 percentage or 1 percentage or 10 percentage, whatever it is a number given in the problem. If your p-value is tinier, if your p-value is smaller, and if it falls in the rejection zone, that means you're going to reject the statement on you. On the flip side, if your p-value is bigger than alpha, that means you fail to reject the statement on mu. That means your statement on mu is good to go. But still, when it comes to the conclusion part, you are going to be writing based on the claim. Okay? All right. The next one we have seen how to select the alternate hypothesis, because I told you that in this Math 130 level, the beginners level class, you are going to have mu equal to mu sub 0. That's always going to be there. But how we are going to be playing only with the alternate hypothesis. The alternate hypothesis could be less, greater, or not equal to. How to choose the alternate hypothesis? For that, again, you have to read the problem. So the problem will give you the hint about the less than, greater than, not equal to. If it is related to less than, you will see the keyword less or below or lower or shorter or smaller or decreased, reduced. All these phrases are going to be there in your less than mu sub 0 alternative hypothesis case. But on the flip side, you will have the wordings greater than, above, higher, longer, bigger, or increased. So these are all going to be the word that will be there given in your problem, and that indicates your alternate hypothesis is going to be greater. All right, coming to the not equal to, so you will see the phrase saying is not equal to, is different from, has changed from, is not the same. So these are all the wordings that you will see in your problem, and that indicates your alternate hypothesis is going to be not equal to. Always the null hypothesis is going to be mu equal to mu sub 0. All right. So then based on the claim, these are all the technical wordings that you are going to be using. You will say, yes, there is enough evidence, there is not enough evidence. So this is how the conclusion is going to be written. And then you complete the sentence based on the claim, okay? But the proper way is to say, yes, there is enough evidence to say. Why, when are you going to say that? When your null hypothesis the claim, and if you are going to get a stronger p-value, stronger the p-value, you see a strong evidence to keep your statement. If your probability is going to be weaker, that means you are going to be rejecting your null hypothesis, because the p-value is going to be falling in the rejection zone. So that way you are going to reject your null hypothesis on you. All right. So this is the overall picture of chapter 14 and 15. So once you confidence limits, I'm sure 100% you got the confidence limits, and you are going to use your TI to get the confidence limits, and I showed it to you. And then for fine size, do the numbers in geometry is equal to z star sigma over margin of error the whole square. And again, the testing of hypothesis, everything is in here, which is going to be move on test and says Z test. Okay. So your life is going to be much easier with the TI. You don't have to think by hand. My blah blah is done, and have you any question, I can answer your question. Otherwise, we can still go and complete the rest of the worksheet that we started yesterday.
Any question?
Yes, go ahead.
Are we going to be learning about power in this?
Those were advanced. So power is going to be our beta, because this is already a 6-week course. It's not going to be included. So in chapter 15, finding the sample size, you are also given, besides finding the error, all advanced classes. So don't worry about